In this video, I'll be covering more advanced memory concepts. These concepts will help solidify your understanding of how Rust utilizes memory and why we need to take certain actions in Rust under specific circumstances. Before we hop into more advanced concepts, let's have a quick recap from the intermediate memory video. All data has a memory address, and these addresses determine the location of the data in memory. Offsets can be used to access adjacent addresses, and these are also called indexes or indices. So this means we can access data before or after the memory address by using an offset. There are two ways that memory is managed by a system. The first is called a stack. Stacks have their data placed sequentially, so everything is packed right next to each other. There is a limited amount of space available on a stack. When writing programs, all variables you create are stored on the stack. This does not mean that all the data is on the stack, just the variables. Stacks are super fast to work with because they use offsets to access data, which just requires adding or subtracting a number from the memory address. Let's take a look at a visualization of a stack in memory. Here we have some contiguous memory, and each color represents some different data. The top and bottom halves of the slide are the same memory, just represented differently. The one at the top goes from left to right, and the one at the bottom goes from bottom to top. Here are the addresses for this chunk of memory. The ones that are highlighted in white, these are the ones that signify the start of some new data. As you can see, the data is packed without any gaps between items. So we just go from one piece of data onto the next piece. There's no memory gaps in between. Since we know the size of these chunks of data, that one's 3 bytes, this one's 4 bytes, we can jump from here to here, and we'll be at the beginning of a new piece of data. So we'll have the beginning of this one, and then we could jump to the beginning of this one. And then we could jump again to this one. Offsets are used to jump between pieces of data. The implication of this is we need to know how many bytes are occupied by each piece of data. We know that this first piece of data is 3 bytes, so we can easily jump from here to here and then start accessing the second piece of data. However, if for some reason the compiler thought that this was 4 bytes instead, we would jump from here to access the second piece of data, and then we would start accessing it from the second byte, and this will result in data corruption. Knowing the size of the data ahead of time is important, that way we can utilize offsets. This is why vectors only allow a single type to be contained within, because it uses offsets to jump between data, and if everything is the same size, then it can quickly and efficiently jump to any element within the vector. One last thing about stacks. It's only possible to remove items from the top of the stack, here. So we can only take something off here. If we were to remove this one, then we would just have empty space and we couldn't reclaim it because we're not able to move things around. So we can't just move things around however we want. It has to be removed from the top and then added to the top. So if we remove this, then we can add something. But if we want to remove this one here, we have to remove this one and this one. So we can only add and take away things from the top of the stack. The other way memory is managed is by using something called a heap. With a heap, data is placed in memory algorithmically. This makes it slower than the stack since the address needs to be calculated. However, the trade-off is we get unlimited theoretical space. In reality, this is limited by your hardware. The heap uses pointers to point to where the memory is. Pointers are a fixed size depending on the architecture of the computer. 64-bit PCs have a pointer size of 64 bits, for example, and the Rust data type for a pointer is usize. Vectors and hash maps are stored on the heap, along with any dynamically sized collection. This is done because a heap can edit memory anywhere at random, while a stack is limited to adding or removing from the top of the stack. Let's now see how the heap looks in memory. At the top, we have a stack. So here's our stack at the top, and it has 7 pieces of data contained within. Each one of these pieces of data is a pointer which points into the heap. So for example, this one here, this one points to the green one there. To access heap data, first the pointer must be read. So if we use this gray one here, for example, we would need to read that pointer, get the memory address, and then follow that pointer to the actual memory here in the heap. This process is called dereferencing. Once the pointer is dereferenced, then the data to which it is pointing to can be accessed. So if we were to follow this pink one over to here, we'll end up here in the heap, and then we can use offsets to access each piece of data that's contained within that collection. You can imagine these pointers here on the stack as being different vectors, and each one has a different number of elements being managed. If we take a look at the heap, we can see some of these vectors have lots of room to expand, while others have very little room. So this orange one, for example, only has room for one more element, whereas this green one has lots of room to add more elements. If a vector runs out of space, the memory can be copied elsewhere, and the pointer on the stack can then be updated to point to the new heap location. So if we wanted to add 2 more elements to this orange vector, we only have room for 1. So what will happen is this entire vector will get copied somewhere else, and then the pointer will be updated to point to this new location right here. And then you'll have more memory available to increase the size of your vector. This all happens automatically behind the scenes, but it is important to understand so you know the implications of storing data on the stack versus on the heap. It also helps when you're writing algorithms and data structures to be aware of the trade-offs between the 2 memory access mechanisms. Let's take a look at a quick example of placing some data on the heap. All we have is just a struct named entry, and it has an ID. On this first line here, we're creating a new entry with an ID of 5 and just naming it data. On the next line, we have a data PTR, and that's just short for data pointer. We're using a type annotation here. This usually isn't necessary. However, you'll see this box a lot when you're working with code, and box just means we're putting it on the heap. To put this data onto the heap, we use box new to create a new box. We then box up this data, and it will be moved onto the heap because box just represents a pointer somewhere on the heap. If you want to move this data back onto the stack, what you can do is use an asterisk to dereference the data. So we'll use an asterisk with the data pointer, which is a box. Once we do so, the data will be moved back onto the stack. It's really that simple. Occasionally, when you're writing Rust code, you'll get an error about sizes. Specifically, it will state that we don't have a size that's known at compile time. The reason we get this error is because the size of the object may be different when you run the program, and it's unable to store it on the stack. Therefore, the fix would be to box the object and store it on the heap. That way, the stack will just have a pointer, which is always usize. Normally, this will fix the error. To recap, for stacks, they have sequential memory addresses. They're used for all variables in your program. They do have a limited size, and it is important to know the size of the data ahead of time. That way you can properly utilize the offsets. With a heap, the memory addresses are algorithmically calculated. It's used when you're working with large amounts of data. It has theoretically unlimited size, and you can store dynamically sized data or data where you don't know the exact size.